Alright, so in this problem I have this green plate right here. It is pinned at the bottom left corner, so it is free to swing about that pin joint, except for the fact that initially this thing is suspended from the ceiling by the string right here. So what I'm going to do is I'm going to cut this string like so. As you can imagine, this thing's going to start rotating about the pin sort of clockwise. Now this pin joint, although it allows the plate to rotate freely around the pin, it does keep that plate fixed in space. So in other words, if I were to draw the forces acting on the pin, I'd have a vertical force like so, keeping the pin from moving up and down, and I would also have a horizontal force pushing left or pushing right. I'm not exactly sure which way it's pushing. So that vertical force I'll call Py in the j-hat direction. The horizontal force I'll call Px in the i-hat direction, horizontal. Alright, so here's my first question for you. Immediately after the string is cut, I mean immediately after, right after we cut the string, which way does the horizontal component of the pin force act? That's this Px. Does it push to the right? Does it pull back to the left? Or is it zero? Now my second question has to do with the vertical component of this pin force. That is, how does that vertical component, Py, compare to the weight of the plate? Is Py going to be bigger than the weight of the plate? Is it going to be less than the weight of the plate? Or is it going to be equal to the weight of the plate? So those are your three choices for question number 2 here. Now I want you to, before we continue this video, I want you to thoroughly consider these two questions. See if you can answer them. Don't answer them based upon your intuition. Instead, can you give a rigorous justification based upon first principles of dynamics to answer these questions? Can you back up your answer rigorously using those principles? That's what I'm really after. Go ahead and think about it. So in this case, I want to construct my argument using Euler's equations for the rigid body. So first thing we have in Euler's equation is that we take the sum of all the external forces acting on the body, and this has to equal mass of the body times the acceleration of the center of the mass of the body. Also, Euler's equations has a moment equation embedded in it as well. And for if we have a body with a fixed point, if it's rotating about a point that doesn't move, like this bottom left corner over here, then we can take the moment about that point, let's say moment about the pin. These are moments due to external forces. This has to equal moment of inertia times the angular acceleration of the body. So here I'm going to use these two principles right here to argue my case. So to work through this argument, what I'm going to do is I'm going to draw a free body diagram. And since I already started drawing forces down here, why don't I turn this thing into my free body diagram, FBD here. And when I draw my horizontal and vertical components of the pin force, I think I got something started here. Let me just draw this horizontal one to the right. And if this, we'll just use that as our initial assumption. And if it's not true, we'll fix it later. But we'll start with that, just so that we have something concrete to work with. So there's my pin force, horizontal and vertical components of the pin force acting on the body. And what other force do I have? Well, remember, the forces are the forces of things that are actually pushing and pulling on this body. We no longer have the string or rope here pushing or pulling on it, so that's gone. But we do have the weight, right? So let's put that in. And the weight acts through the center of mass, right? So we'll assume that the mass of the plate is uniformly distributed throughout this square here. So the center of mass will be right here in the middle of the plate. And that's what I get for my free body diagram. Now for the mass acceleration diagram, I'm going to draw this plate quite a bit bigger just so I can see things a little bit better. Now let's think about, I'd like to think about this moment equation first. Notice that if I look at the moment about the pin joint here, these two forces, Px and Py, they're not going to create a moment, right? Because they act directly through the pin joint. The only thing that's creating a moment about the pin, the point P here, bottom left corner, is the weight itself. And that's going to create a clockwise moment. So let me just sort of draw on this mass acceleration diagram a angular acceleration, or moment of inertia about point P times an angular acceleration. Okay, so this moment here is going to create an angular acceleration, a rotation clockwise. Another thing that goes on my mass acceleration diagram is the acceleration of the center mass. The acceleration of the center mass, as we described, is right here in the middle. And in general, this the center mass could be accelerating left and right or up and down. And how should we think about this? Rather than think about it in terms of its horizontal and vertical components, I think it's easier to think about that acceleration of that center mass a little bit differently. So let's think about this. When I cut my rope right here, what's going to happen? Well, the whole thing, as we said, is just going to start rotating clockwise. What's going to happen to the center mass when the whole thing starts rotating clockwise? Remember that this thing's a rigid body. The distance between the center mass and this point we're pinned at cannot change. That has to always remain the same. Therefore, when this plate starts rotating, the center of the plate, that center of mass, has to move around the pin in a perfect circle, constant radius from that pin, constant distance from that pin. Can't get any closer, can't get any farther away. Has to be a perfectly circular arc that this thing is moving along. Therefore, when thinking about the acceleration of the center mass here, I think it's easier to think about it in terms of path coordinates, or these normal and tangential coordinates, right? So I will have, as this center mass is moving along the path, I will have in general a component of acceleration that's tangent to the path, and also perhaps a component of acceleration perpendicular to the path, the centripetal acceleration, right? So I'll call this tangential component AT, and I'll call the centripetal part AC. So let's look at this. Let's start with this centripetal part of the acceleration. The centripetal part of the acceleration, recall, goes like, remember it's centripetal, it's the speed squared divided by radius, or r theta dot squared if you want to think about it in terms of polar coordinates. Remember my question asked about the forces, the pin forces, immediately after the string is cut. Well, immediately before the string is cut, the plate is stationary. Immediately after the string is cut, hasn't built up any velocity yet. There's no angular velocity yet. So immediately after the string is cut, this plate is not rotating. Immediately after the string is cut, theta dot has to be 0. So therefore, this centripetal acceleration has to be 0. And therefore, I do not have this piece right there. No centripetal acceleration whatsoever. Let's look at the tangential acceleration. That tangential component, this one goes like r theta double dot. So here's r theta double dot. This is a time derivative of the angular velocity, the time derivative of the rotation rate. It's the rate at which the rotation rate is changing, if you will. This is the angular acceleration. Because I have a moment, I do have an angular acceleration. So this thing is definitely not 0. My angular acceleration is clockwise. So therefore, this point right here is accelerating along the path, tangent to the path, so clockwise. At this instant, the instant the string is cut, this thing is accelerating downward and to the right. Downward and to the right. So just to be emphatically clear, let me erase this centripetal part. It's not there at all, right? It's not, the plate is not moving immediately after the string is cut. All we have is this tangential acceleration. It's downward to the right. So given that, let's look at this force equation that we have. In the I-hat direction, the horizontal direction, my external forces are I only have the px in the I-hat direction, right? So I got px. And this has to equal mass times the horizontal component of the acceleration of the center mass. And look at this acceleration of the center mass. It has a vertical component downward, and it has a horizontal component to the right. So the horizontal component of this acceleration of the center mass is that way. Therefore, px must be that way. This force px has to be pushing to the right. There's your answer to the first question. Horizontal component of the pin force has to be pushing to the right because the center of mass is accelerating to the right. Now, in my experience, most students tend to say that this px has to be 0 immediately after the string is cut. It's not 0. It has to be to the right. Alright, so let's start thinking about the vertical component of this now. My vertical components say I've got py pushing upward. That's from the pin force. I have the weight pulling downward. I'll write the weight as mg. And this has to equal the vertical component of acceleration, right? So mag y right there. Now here's the trap that many students fall in. They start thinking about this from a statics point of view rather than dynamics. They look at these forces. I got a Py pushing up and a weight pulling down, and the statics point of view says these forces have to balance, right? So you take all your forces, and if you're in statics class, what you do is you set all these forces equal to 0. Now if this were the case, and it's not, but if this were the case, then Py would exactly balance the weight. And therefore you would say that the vertical component of this pin force has to equal the weight, right? This is a statics way of thinking, not dynamics. This thing is moving, it's accelerating. So Py equaling the weight is not true. So let's think about what's going on. I've got Py pushing up. I've got the weight pulling down. Again, if there was no acceleration on the right-hand side, then these two forces would exactly cancel each other out. But they don't cancel each other out. They add together to equal an acceleration that has to be downward, right? So you take this vector upward, that vector downward, and it has to produce something that's downward. What's the only way that can work out? The only way that can work out is if Py is, well, first of all, the weight's constant. I can't change that. That's fixed, right? So the only way this thing can work out is if the force upward is smaller than the force downward. That's the only way you can get an acceleration downward. So therefore Py has to be smaller than the weight. So there's your answer to the second question. And that'll do it.